to the 6th session on electrolytic conductance. In this, we will be seeing the experimental determination of transport numbers by another method known as the moving boundary method. As you all know, transport number is the fraction of the total current carried by a particular ion. Before going into the details of this experiment, we will have to see two laws based on electrolysis. First one is the first law of Faraday's law of electrolysis. Here, the mass of a substance deposited or liberated at any electrode is directly proportional to quantity of electricity passing through the electrolyte. And what is quantity of electricity? It is strength of electricity multiplied by time. The current strength I should be in amperes and time should be in seconds. The product of these two is known as quantity of electricity, and the amount of substance which has been deposited on an electrode or which has been liberated in an electrolysis process is directly proportional to the quantity of current passed. If you increase the quantity of current passed, the amount of substance deposited or liberated increases, and if you decrease, the vice versa happens. Now, this proportionality can be made as an equality where W is equal to a proportionality constant Z into I into T. Now, this proportionality constant Z will be equal to W when I is equal to 1 and T is equal to 1, or you can say that if a current strength of 1 ampere is passed through an electrolyte for 1 second, that is when I is equal to 1 and T is equal to 1. Here, if these two are unity, naturally W will be equal to Z, and this Z can be defined as the amount of substance deposited or liberated when a quantity of current of 1 coulomb is passed, or you can say it as 1 ampere of current strength for 1 second. Okay. So, ampere into second is known as coulombs, which is also another unit. You can either say that is 1 coulomb of electricity is passed or 1 ampere for 1 second, and this proportionality constant is named as electrochemical equivalent, and here it is denoted by the letter small letter Z. So, electrochemical equivalent is defined as mass of the substance deposited or liberated at an electrode when a current of 1 ampere is passed for 1 second, or you can say 1 coulomb of electricity is passed. This is the first law. Now, let us move on to the second law. In second law, when same quantity of electricity is passed, that is the condition, same quantity of electricity is passed through different electrolytes. So, you are going to pass the same quantity of electrolyte, but through different electrolytes, the masses of different substances that has been deposited or liberated at the respective electrodes are directly proportional to their chemical equivalents. So, how much of the substance get deposited or liberated when the current passed is constant? It is in the ratio of their chemical equivalents. What do you mean by chemical equivalents? That is their equivalent masses. Okay. This can be expressed like W1 by W2, that is mass of a substance 1, E1 represents equivalent mass of that substance 1, W2 stands for mass of the substance 2 and E2 stands for equivalent mass of the substance 2. Therefore, W1 by W2 is equal to E1 by E2. This is the second law of Faraday's laws of electrolysis. Now, from Faraday's laws of electrolysis, there are certain points to be noted. That is, quantity of electricity required to deposit 1 gram equivalent of any substance will be a constant. If you are going to deposit only 1 gram equivalent, that quantity of electricity will be constant. and it is 1 Faraday, that is the current required to deposit or liberate 1 gram equivalent of any substance, and its value is found to be 96,500 coulombs. So, if I put 1 Faraday of current through any solution, you can have 1 gram equivalent deposited or liberated. Okay. Now, we will move on to the experimental part of moving boundary method for determination of transport number. Here, the moving boundary method. Here, we have to follow the motion of the ions to any of the electrode just by observing the movement of a visible boundary between the two electrolytes, and that is how we are going to calculate the transport number of an electrolyte. Now, the apparatus used is like this. You are having a tube which has got two wider ends at the both ends. On one end we have the platinum electrode, the other end we have the cadmium electrode, and here we take two electrolyte. One is HCl, whose ionic transference number of H plus ions are to be determined, and you have another electrolyte that is known as cadmium chloride. Okay. Just remember, we have been saying that we have two electrolytes HCl, and this is known as principal electrolyte, and cadmium chloride is known as the indicator electrolyte. We have been using the same thing when we have to determine the ionic mobilities. Now, what are the factors that determines a principal electrolyte and an indicator electrolyte? Both should have a same common anion, and the mobility or speed of H plus ions should be faster or should be greater than that of cadmium 2 plus. So that when cadmium moves, it will be following the H plus ions, causing a sharp boundary which moves up. Okay. Then this is the negative electrode and this is the positive electrodes. In both cases, the chloride ions will be moving down towards the positive electrode. Now, what happens is, when we fill this tube first with cadmium chloride and then with HCl solution, the HCl solution floats over cadmium chloride because it is less dense and showing a sharp boundary which is denoted by AA dash. Once we start passing the current, since the H plus ions move forward followed by cadmium ions, the boundary moves from AA dash to the position BB dash in the tube. Okay. Now, let the length of this be L, that is from AA dash to BB dash be L centimeter, and area of cross section be A centimeter square. Okay. Now, this is connected with a coulometer. It can be either silver or copper coulometer, from which you can find out the total quantity of current passed, that is Q, that is the total quantity. Current passed. Now, with these observations, you can determine the transport number. Let the volume through which the boundary has moved, that is, it has moved a distance of L across a cross section of A. So, that makes a volume of L into A centimeter cube, where L centimeter is the length and A centimeter square is the cross section, where L is the distance moved and A is the area of cross section. If the normality of HCl taken in the tube contains C gram equivalents per liter, the number of equivalents of H plus ions, which will be equal to number of equivalents of HCl moved under the applied current, is equal to, that is, you are having the concentration C gram equivalents per liter, and we have a volume of L into A centimeter cube moved, and therefore, number of equivalents will be L into A, that is a volume, into C by 1000. That will give you, because C by 1000 means that is the number of equivalents divided by, which is dissolved in 1000 cc. So, you get the number of equivalents per cc multiplied by the volume in cc through which the boundary is moved. From Faraday's law of electrolysis, we know that for 1 gram equivalent of any substance, we require 1 Faraday, that is equal to 96,500 coulombs. So, if so much equivalents have moved, what is the amount of current carried is equal to L A into C into F, which is Faraday by 1000. And if total quantity of current passed is Q, and then this is the current carried by H plus ions, okay, current carried by H plus ions, and this is the total amount of current passed, and therefore, this divided by total current will give you the transport number of T plus, that is equal to LACF divided by 1000 into Q. Now, let us see a problem based on this. Here we are having a moving boundary experiment having 0.1 normal KCl solution, and the boundary moved 4.44 centimeter during a time of 70 minutes when a current of 5.2 milliamperes were used. The cross sectional area of the tube was 0.25 centimeter square. Calculate the transport number of K plus ions. Now, here we know that the expression is T plus is equal to L into A into C into capital F divided by 1000 into Q. Now, what is L? L is equal to, that is the length of the cube. The cross section area A is equal to 0.25 centimeter squared, that is length is 4.44 centimeter, and time is equal to 70 minutes, which is equal to 70 into 60 seconds. Current passed is equal to, I is equal to 5.20 milliamperes, that can be again converted into amperes into 10 to the power minus 3 amperes. Okay. And the concentration, right, C is equal to 0.1 normal. Okay. Now, all the values are obtained, you can apply that in this. L is equal to 4.44 into A is equal to 0.25 into C, that is equal to 0.1 into F, that is equal to 96,500 divided by 1000. Now, Q is missing. Q is equal to I into T. I is 5.20 into 10 to the power minus 3 into 70 into 60. So, I can apply it here, 5.20 into 10 to the power minus 3 into 70 into 60. And by solving this, you will get the value of K plus as 0.4904. So, that is the transport number of T plus. They have not asked for the Cl minus. If they ask for Cl minus, you subtract the value from 1 and you will get the T minus value for the Cl minus. So, in this session, we have been seeing Faraday's first law of electrolysis as well as second law of electrolysis. First law states that the amount of substance deposited or liberated is directly proportional to quantity of current passed through it. And second law states that if same quantity of current is passed through different electrolytes, the amount of substances deposited or liberated at the respective electrodes is in the ratio of their chemical equivalence. And next, we have been found the experimental determination of transport number with another method known as moving boundary method, from which you can calculate the transport number of a cation T plus is equal to L into A into C into F divided by 1000 Q, where L is the distance through which the boundary is moved, A is the area of cross section of the tube, C is the concentration, F is Faraday, which is equal to 96,500 coulombs, and Q is the total quantity of current passed through the electrolyte. And thank you.